So 30-degree angle, 1 kilogram part. What is the K value of the spring? And we know the total mechanical energy is 16 joules. Got 2. We almost ready? Not quite.
Is it 3?
Yes,
Wow.
it sure is. Very springy. And what?
That's no.
Yes.
Yeah.
I lost it. I bought it, but then I lost it. So what I did was that solve for H, and then I could plug in that the 1/2 kids 3 squared is equal to 16 joules. Yeah. So it's
Oh, for the spring, E is where it's not stretched or condensed, and we know that because there's no spring potential in it.
I got negative. Mrs. McAleer, is it supposed to be negative?
No,
I think I coincidentally got it by doing. That was an accident. I somehow got a negative. I don't know quite how. Maybe.
all right, how about this? How did we find the height, Faith? Did you find the height? Grace, did you find the height? Okay, we know that at point E, all the energy is gravitational, right? We know that from the bar chart. So 16 joules is equal to 1 kilogram times 9.8 times height. And so when we solve, we get height is equal to, not meters per second, just meters, 1.6 meters, right? Okay. Next, I want to find what is the K value of the spring. Where do you think I should figure out the K value of the spring? Like what location should I be doing a calculation for? A, why, Nathan? Because we know E equals 16 and I don't have to consider anything else. Everything else is minimized, right? So I know at point A, so this is at point, okay, I can't spell, P-O-I-N-T-E. This is at point A. It's going to be the spring potential is equal to 1/2 kx squared. So spring potential is 16, 1/2 k. Uh-oh. What is my x?
It's 0.806.
It is not 1.6. This height is 1.6. This angle is 30. How do I find this distance? So when I take sine 30, right? Sine 30 is equal to opposite 1.6 over this hypotenuse, which is the height or the x value I was looking for. So 1.6 divided by 1/2 is 1.6 times 2. Is it 3.2? Okay. So when I do 3.2 squared, and I solve for k, what do I get? 3.1. What are the units? It's a Newton over meter, right? Yep. No.
What?
Ah. Got it. Christian, you good? Did you do this?
I didn't do it, but I got it.
What are you doing? You're doing what?
First, yeah, I should have done the.
Okay, can we do personal stuff on personal time, not my time? Thank you. Okay, questions on any of this? Energy, oscillations before we move on?
Your calculator is supposed to be in degrees, right?
Yes.
Oh, okay, that was my problem.
That's why Bobby was having a little.
Wait, no, but isn't it 3.2 divided by 2?
Tourette's.
Because
Brilliant.
isn't it 3.2 divided by 2 because C is the equilibrium point? So when
No,
you stretch it down.
C is not the equilibrium.
E is the
the equilibrium point. It explicitly states that in the problem.
You have a showdown.
Harsh. With a target C though.
No, that's just where the picture is from. Equilibrium point is it.
No, part and to the rest of it.
Yeah, I know. If you add a mass to it, the equilibrium point is it.
The natural length of the spring without the cart is at point E. So E is where it is when it's not stretched or compressed.
Add the mass. That's what it's called.
Okay, let's talk about pendulums. What's a pendulum?
It is a swing.
Something that swings.
And oscillating.
It also oscillates. Pendulum. Okay. Workbook problems. We did that. Okay. So here is what we're going to do. I have a pendulum, right? What? No. When I want to know what I can do to change the period of the pendulum. So when I say the period of the pendulum, what am I saying? The time it takes to go from here to here, right? So one complete cycle, the time for one complete cycle is the period. By the way, what's the relationship between period and frequency?
1/n.
Inverse, right?
Can I get my notes?
Yeah. Oh, not right now. I mean, do you need them right now?
So that's where I was gonna take notes on.
Can you do it on a separate piece of paper? I'll do it to the end. Okay, so period is 1 over the frequency. We know that. So now, first of all, what are things I can do physically to this that could change? Like, what are things that you might want to test out? Like, what do you think we could do that might change the period? I could add mass, so I have more mass. What else could I change? Yeah,
Increase or decrease the length of the string.
I could change the length, so I could make it longer or shorter. Okay. There's this- One of these things makes it right there. I can make it longer and shorter. Okay, is there anything else you want to test? How about instead of force applied, that's basically saying like how far back I bring it, right? Because by the way, what is the reason it swings? Okay, gravity is considered the, but what is the weight force?
Energy.
Okay, what is the weight force trying to do?
Hold down.
Take it back to equilibrium. What do we call a force that brings it back to equilibrium? A restoring force. By the way, is the entirety of the weight force the restoring force?
No, just the component of this.
Because here's mg. Here's the tension. there's a component of the weight force that is trying to bring it back to equal. Right? Okay. So let's go through, and we've talked about the three things we want to change. We want to change the mass, we want to change the length, we want to change the amplitude. I need you guys to go get a phone or a way to measure a time. Go get a timer, whether it's a phone, something on your computer. I need everyone to get some way to measure time. Yes, we're doing a lab as a group lab. Okay, what do we want to test first? What do we want to test first? Amplitude, mass, or length?
Mass.
Mass. Okay, so for the mass, we're going to start at the, because we want to keep everything else the same. We'll consider this to be like small amplitude, right? And this to be small length. So I'll change the mass, keeping everything at the small. And then I will increase, we'll compare the amplitudes, and then we'll increase the length, okay? So we're gonna stay at this. Go a little smaller, how about that? Okay, so we're gonna do the mass first. So this will be our small mass, and then I'll add this to make it a large mass. What do you think we should do to decrease error?
Set a physical point for how far to pull it back.
Yeah, I'll line myself up with this. There we go. What else? How many periods are we trying to find ultimately? Maybe we should run multiples. Do you think it's easier to run multiple by me stopping every time, or just let it swing? Okay, so how many swings are we going to count?
10.
10, I like 10. Let's do 10. It even says it on the board. We're gonna do 10 oscillations. Why are we doing 10 oscillations? To reduce error, right? So we're gonna count to 10. We're gonna start it We're gonna count 10 full oscillations, and then how do you find the length of one period? Okay, so we're all doing it. So everyone has a time device? Okay, so 3, 2, so I'm gonna go 3, 2, 1. Let me see. When am I gonna do it? 3, 2, 1. I'm gonna release on go. So it's gonna be 3, 2, 1, go. I'm gonna do the same pace, and I'm gonna release on go. Ready? 3, 2, 1, go. Three, 5, 6. Am I counting right? Did I miss one? 7, 8, 9, and 10. Do we all stop it? Okay, divide by 10. What did we get for our small amplitude? Okay, we're just gonna go around. So Nathan, what'd you get?
All of them?
No.
I did it wrong too.
I got like 2.
Did we not know we were doing? You get one number and you divide by 10. You can do that in your head. Move the decimal.
I got 2.467.
2. Small amplitude. 2.4. What's another one we got?
2.46.
2.4. What's another one we got?
2.46.
2.5. What'd you guys get? 2.4 and 2.6? Is that, Nick, you had 2.4, right?
Yep.
Nayland had 2.6. What on average are we seeing?
2.4.
2.4. All right. So now we're going to do a bigger amplitude.
Does that also count for small mass as well? Those numbers?
Sure, we'll get there. Let's do one thing at a time. So yes. Okay, so do you agree this is a higher amplitude?
C.
Okay, are you ready? Do we know what we're doing this time? We're counting to 10. Can you count to 10? Eloise can count to 10, guys. Can you count to 10? All right, ready? 3, 2. 3, 2, 1, go. 1. Oh, I forgot to ask suggestions. I'll count. How many people think that it's going to be bigger? How many think it's going to be smaller? How many people think it won't change? Okay. How many people are chickens and won't? Is this 9?
Yeah.
And 10. All right.
I got
2.5. Yeah, I got 2.5.
I got 2.2.
Not literally exactly
2.5.
I waited a second, so.
2.5.
Well, no, I stopped.
All right. What are we thinking?
I got
It's about the
2.6.
same. 2.5.
It's about the same. So does amplitude make any effect on the period? No effect. All right. As Sam said, we can use this same 2.4. Now that we know the amplitude doesn't matter, do I need to even have a reference point? Not really. Can we consider this is my small mass? I'm not changing the length. So small mass, we can just say it's 2.4. Let's add a mass.
The small line as well.
I told you we're doing one thing at a time. Let's. I need a hint. Can you thread this through? Okay, and then flip it there. Turn it. And then clip it. Don't change the length. Clip it to the hook. On hook. Be nice. Go sit down. Okay, we're gonna do it this length. That's okay.
Is that a long way?
That's gonna be our big one.
This will apparently be our big one.
I don't know. It's a little short.
Oh, but now I don't want to change multiple variables.
Yeah. Do we know exactly how long? the
So
short
maybe
length
we
was?
should.
It's
test the
okay.
length
We'll
first.
just test it again.
Oh,
Okay, here we go. This is going to be,
Big mass, big one.
Why don't we change it to-
we're just gonna consider this to be the big mass. Okay, we're going at 10, right? Are you ready?
Oh, no, no,
3.
no.
Well, you weren't texting.
All right, ready.
3, 2, 1, go. 1, 2. Almost as fun as AP2. We have a lever we literally watch wider coil for 45 minutes. It's my favorite lab. It's our group therapy session. We talk about our lives. I'm excited. And 10. Do we get it?
2.8.
2.8.
Yeah, 2.8.
All right. Big mass. 2. I'm bringing a lot of 2.8. Are we just gonna
2.8.
2.8? So let's keep it at this length and take this mass off.
And now the.
Because now we know something, either the length or the mass changed it, right? Do you agree? It was either the mass. Grab the mass. Thank you. Okay, so this is going to be at the same length, right? Same length here. Now we're going to try small mass. Yes, I know it will count for other things, but just hold your horses. Okay, so we did big mass. Let's do small mass. Do we agree this is the same length?
Wait, so this is how it is small mass and. big
I
mass.
just said.
I'm just replaying things in my head. That's it.
Here we go. We're gonna go in 3, 2. Dalen, hurry up. 3, 2. Are you ready?
Yeah.
3, 2, 1, go. 1.
6.
Spanish. And
Yes.
yay!
2.8.
Oh, so what's in the mass?
Was the length.
It had to have been the length. Because now we can compare my small length with no mass is like the 2.4, right? My big length with no mass is 2.8. At the length that we did it, the small mass is 2.8. So did the mass have a change? No effect. Does the length have an effect?
Yes.
It's the only thing. Actually, it's not the only thing. There's one other thing. Now think a little bit critically. What else could I change that I can't actually change that would affect this?
The resistance.
Yes, the force, right? The restoring force. If I increase the pull of gravity, does that increase my force? Does that change my period? Yes. So if I were, able to turn up or turn down gravity, which, we can't just go to the moon right now. So there you go. It would be. All right, so for a simple pendulum, right? Simple pendulum is a particle of some mass m attaches to a frictionless pivot cable with a mass length L. So the L here is from the pivot point to the end here. If my cable is pulled away, does the angle matter? No, we've determined it does not matter, right? I could go small, I could go big. So if the angle doesn't affect the period, does it affect the frequency? No, right? Because period and frequency are inverses, so the period doesn't change, frequency doesn't change. Okay, the pendulum is swinging, right? Because of the torque provided. So we can either treat this as a rotational problem and say, hey, there's a component that's pulling towards equilibrium. We could also treat it as like a linear problem and just break it into all the components. Either way, there is some component of the weight force that pulls it back to equilibrium. We call that the restoring force, right? The weight is providing the restoring force. So my period is equal to 2 pi square root of the length divided by the gravitational pull, right? Is amplitude in there anywhere? Is mass in there anywhere? Those things don't affect the period. Length. If I increase the length, what does it do to the period? Increases it. If I increase the pull of gravity, what does it do to the period? Decreases it. If I increase the length, what does it do to the frequency? Decrease. Because period is 1 over frequency. So if I increase the length, it increases the period. If I increase the period, it decreases the frequency. If I increase the weight force, what does it do for the frequency? What? Decreases?
You can decrease that, it makes it bigger. Yes.
So one more time. Don't say anything. If I increase gravity, don't say anything. What does it do to the frequency? Show me. Increase or decrease? If I increase this, it decreases this. If I decrease this, it increases that. So increase. Yes. Good. Good. Okay. Example. A clock often uses a pendulum to keep time. Determine the length of a single pendulum that will swing back and forth in simple harmonic motion for a period of 1 second. By the way, doesn't matter what my mass is. No, but the length does. So find for me what length.
Can you write the equation on the
This is on your equation sheet, by the way. The other thing on your equation sheet, actually, side note, the period of a pendulum sub p is 2 pi over root L over G, which we have, right? The period of a spring, right? What is going to affect these springs going back and forth? In that case, the mass does matter, right? And the K value of the spring. So it's 2 pi root M over K. So if I increase the mass, what does it do to the period? Increases it. If I increase the K value, what does it do to the period? Decreases it.
I get 0.24. Yeah, I get 0.24.
This is period. T for period is Q pi root L over G. Okay, did we get 0.248? Okay. I feel like this is redundant. What variables affect? Okay, cool. We'll just end there. All right, we will do our lab tomorrow. Yay. Are we all good? You will have a period of a spring on your test, and we're not talking any more than we just did. That was our lesson on spring oscillations as well. It's the same pattern, except it's M over K instead of L over G for a spring. It's on your equation sheet. It makes sense. Yay. All right, guys, have a good day.
Yeah.